As an example of problem formulation, let's consider the 8-queen problem again. So it's a game. And in this game, we start with an empty board. And the players take turns into putting a queen on the board. And the goal is to have a board with 8 queens on the board where no one is attacking another one diagonally, vertically, or horizontally. So the state is any arrangement of 0 to 8 queens on the board. And we know how much is this. This is 68 times 67 times 57 possible arrangement of having 0 to 8 queens on the board. The initial state is having an empty board in which no one put a queen yet on the board. The actions is simply each player adding a queen on the board on an empty square. So these are the possible valid actions. You can't, for example, push one queen and replace it by another one. The transition model is the updated board. And finally, the goal test is a test that allows us to say whether the 8 queens on the board are none of them is attacked. So it's a test that compares each queen with respect to the other ones and says whether the goal test is found and there is no one attacked, no queens attacked by another one. Another famous story example in search problems is called the 8 puzzle, in which we have a puzzle. It's a board of 3 by 3. And the idea is to, and each square has a number, except one of them, that's 3. It's possible to move the squares around. So the idea is to start with some initial state and reach a goal state. So here's a possibility. So for example, we could start with this first board on the left that has actually the number 0 to 7 not in order. And we want to be able to move the squares around until we reach the goal, which is the numbers ordered from 0 to 7, starting from this middle top square. So this could be a possible start state, and this could be a possible goal state. Let's now formalize the problem of the 8 puzzle. So first of all, what are the states? The state is any configurations of the 8 tiles on the 3 by 3 grid. So the location of each of the tiles in the 3 by 3 grids represent the possible states. The initial state is any state we want to start with. So this is a possibility of an initial state in which we have this configuration of numbers on the grid. But it could be anywhere we start. The action is we have only 4 possibilities. Here is to move left, right, up or down. So because of the shape of the grid and the fact that there is only one square that's empty, we could only do this kind of possible actions. A transition model is given a state and an action, it will return a resulting state. So if you are in the state and we move the 0 to the left, we are transitioning the state from one state to another one. The goal state, in this case we picked this to be a goal state, is a state that actually matches the goal. So whenever we are exploring the search space for ways to move the tiles, we're going each time to test when we reach a state in the game whether we are reaching actually the goal state. The path cost finally is the total number of moves. We want, for example, if you want to organize this tiles by increasing order from 0 to 7, we don't want to spend a long time doing that. So this can be assessed by the number of moves. So the total number of moves, where each one costs 1, could be an assessment of how well we are doing in reaching the goal. A typical applications of search agent is routing problems. So suppose we have a map on which we have cities, and you want to go from a city to another one. So you need to use a search agent that helps you find your route or your way going from one city to another one. So this is an example of the North America cities that actually is inspired by the example of Romania in the book from Russell and Norvig. So we picked North America in our case. So suppose we are in the city of Boston and you want to reach the city of Denver. Can you help me find a path or way from Boston to Denver? So a search agent typically will search for possible successful path that will lead me from Boston to Denver. So it could be, for example, this path here, right? It could be going this way, or it could be going that way, right? So the different ways, different paths that lead from the point A to point B. All right, so typically let's formulate the problem. In this case, we have the state is being in any of the cities on the map. So cities could be Los Angeles, San Francisco, Denver, New York, Boston, etc. The initial state in our example, I'm in Boston, I want to reach Denver. So how can I do that? My initial state is being in Boston, right? And the actions I can do if I'm in Boston, So this is here, is to go to New York or to Montreal. So these are the two possible actions, but you can also, in any other state, you could go to Salt Lake City. So going in any city is an action, a valid action in the problem. Transition model tells us if we are in a city and we go to another one, where we end up. So for example, the result of being in Boston and going in New York brings us to being in New York, okay? The goal test is be in Denver. This is what I want to achieve. I'm in Boston, I want to get into in Denver. The path cost, if I want to not spend a long time, because you have seen that there are many ways to go from Boston to Denver, is to count, for example, the path length in kilometers. So how much did it take me to go from Boston to Denver? And we want to have, we could think about getting the solutions, but getting also the solutions with the least cost or the least number of kilometers.